We just talked about this idea that you can go from force to potential, but that also you can go from potential to force by taking a derivative, and we did a couple of examples of that with gravity and with a spring, where we know what the energies are, and therefore I'm claiming you can find the forces. There's a bit of a problem here that it was hinted at in the last video, and part of it has to do with the fact that we need a vector here, and then part of it has to do with the fact that in general, potential energy actually is not just a function of one variable. It often is a function of all of the position variables in the system. So the question that we're going to ask in this video is, how do we deal with this in a general case, and how do we come up with these unit vectors when we're going from potential energy to force? And I'm going to start with the answer and then talk a little bit about what the answer means. So in general, if I want to find the force that some conservative field exerts at some position, the way that I do that is by taking the negative gradient of the potential energy. Okay, what the heck does that mean? So you may or you probably have not seen this upside down triangle before. That's something you'll see a fair bit of next semester in Linearity 2, but it's worth starting to look at now. So let me blow this out a little bit for Cartesian coordinates, and I'm only going to do this in Cartesian right now. So the gradient operator in Cartesian coordinates is the partial derivative with respect to x, I hat, plus the partial derivative with respect to y, j hat, plus the partial derivative with respect to z, k hat. And so if I actually go ahead and write that out, what I get is minus the partial of the potential with respect to x, I hat, minus the partial of potential with respect to y, j hat, minus the partial of potential with respect to z, k hat. Okay, so now we've traded an upside down triangle for these partial derivatives, and those at least should look somewhat familiar, although it's likely you haven't seen the partial derivative before. You've probably just seen the sort of d by dx as opposed to this sort of Greek delta by delta x expression. So let's talk a little bit about what that actually means, and in particular what it means to take the partial derivative of some function. So when we take the partial derivative of some function that depends on multiple variables, right? So we've got, say, the potential, which depends on x, y, and z, and I want to take the partial derivative with respect to x. What this is equivalent to, or a way to think about this, is I'm taking the derivative with respect to x while holding y and z constant. Okay? So I'll give you a couple of sort of simple examples of that. So let's think about the function v is equal to x times y. Okay? Now, if you think about what that function looks like, we could sort of draw the xy plane, right? And we could think about what x times y looks like. Well, pretty clearly, x times y is going to be positive up in this quadrant, right? Because both x and y are positive in that quadrant. It's going to be positive in this quadrant because x and y are positive, both negative in this quadrant. Negative times a negative is positive. It'll be negative here. It'll be negative here, right? When x is 0, right? So all along the y-axis, v is going to be 0, and all along the x-axis, v is going to be 0. And if I think about, say, choosing one particular value of, say, y, so let's choose y is equal to 1. If I were to think about what v looks like along the line y equal to 1, well, along the line y equal to 1, it's just v is equal to 1. For this line, right, v is equal to 1 times x, right? So if I were to actually think about what v looks like here, it's just going to be a straight line that increases, or it's going to increase linearly. So at x equals 1, it'll be 1. At x equals 2, it'll be 2, and so on. If I take a sort of second line of v is equal to, with y is equal to 2, that's along that line, v is equal to 2y. So at this point, if x is 1 and y is 2, it'll be 2 here, it'll be 4 there, and so on. So when I take the partial of this with respect to x, what I'm doing is I'm basically asking the question, what's the derivative of v along some line for which y is constant, right? So if I take the derivative, the partial with respect to x here, then when I take the derivative of x times y acting as though y is a constant, the answer is simply y, right? Because if this were like x times 3, the derivative with respect to x would be 3. Since it's x times y, the derivative with respect to x is y. As a consequence, you can kind of think about what the partial derivative with respect to x looks like for this function. Along the line y equals 1, it's 1, right? So moving along this line, the potential has a slope of 1. Moving along this line, the potential has a slope of 2, and so on. Similarly, I could also ask the question, what's the partial with respect to y, right? Well, that's simply going to be x for this function, which is a way of saying that if I move along a line for which x is constant, then the slope of the derivative of v as I move along that line, right? The slope along that line is simply given by the value of x. So along this line, v is going to be increasing with a slope of 1. Along this line, v is going to be increasing with a slope of 2, and so on. I think I'll make a video right after this to just sort of show what this looks like in 3D using MATLAB, because it's a little bit hard to visualize. So why don't we stop this video here, and I'll kick off MATLAB in the next video.